Okay, so we left off talking about the Bayes classifier, and we had some examples. Let me just pull up my notes. So I updated the notes or the slides. Okay, and basically we left off kind of with this, where we said the Bayes classifier looks like this, and you know what? To save myself some writing pain, I'm going to just go ahead and copy and paste this into my thing that I'm writing up here. Let's push that up there. Yeah, that's good. Okay. So the Bayes classifier, the formula looks like this, and it's basically, this part's the likelihood. It is the probability of getting the data you have observed in your kind of your input vector if you assume that it's from a particular class. And then we multiply that by the prior probability, and that's going to give us the numerator. And then because it's a probability, we know that everything has to add up to 1. And so the sum of the numerators will form the marginal probability that goes in the denominator. And so I think in this example, you know, I have kind of three Gaussian distributions, the red and the blue and the green, and then we're going to just say, what if I put a test case right here at 0, 0? Okay, so to do this, we can punch in 0, 0 and put it into the multivariate Gaussian PDF, okay, which is 1 over 2 pi raised to the number of dimensions, which in our case is 2 over 2, times the determinant of your variance raised to the 1/2 power, you know, the square root of the variance. And basically we are using the MLE estimates of the mean and variance. So from our data, we calculate the mean of class A. From our data, we're calculating the kind of sample variance of class A, all right? And that's going to form our, well, I guess, the unadjusted, the biased version of the variance. And that's going to form our MLE estimates of the mean and the variance. And we plug that in for a determinant. We get the determinant of that, raise that to the 1/2 power, take the square root. And then we multiply that by e to the negative 1/2 times you know, your new value minus the mean, multiplied by the inverse of the variance, multiplied by you know, x minus mu. Okay, and this is kind of you know, if you're familiar with the regular Gaussian PDF for one dimension, it is it's almost the same. It's just kind of in matrix notation, right? Normally you have x minus mu over sigma, where x minus mu squared over sigma, but to kind of get that to work out matrix-wise, you have x minus mu transpose sigma inverse x minus mu. And it's, they're kind of similar, and when you plug all of that in, you get, you know, 0.00777, okay? R has the package multivariate norm, which does the same calculation, but just a lot easier. You don't have to do you don't actually have to punch all of this out. Just like with D norm, you don't have to write out the full equation of the normal distribution PDF. And so we can just use D multivariate normal, put in our new value, put in the mean, put in the variance, right? And so we're going to do this for all 3 classes to get the likelihood. So we take the same point 0, 0, and we compare it using you know, the mean of A, the mean of group B, and the mean of group C, and you know, we can see the likelihood for B is far higher. Okay. As far as the priors, all 3 classes we're going to just assume have equal priors, and so they're all equal and they all kind of cancel out. Not even necessary to include them, but I'll go ahead and do that for completeness. And so the marginal is going to be the likelihood times the prior plus the likelihood times the prior for every single class. So we do the likelihood and prior for class A, likelihood and prior for class B, likelihood and prior for class C, because those are the numerators. And then so the posterior probabilities is the numerator, the likelihood times the prior divided by that marginal probability. And when we do it for 0, 0, which is this picture here, it says class B, so this is class A is red, class B is the blue, and class C is the green. It tells us that its probability that it belongs to class B is like 0.995, which is what we expect, and the probability that it belongs to class A or class C is much lower. I did a couple other examples. So here's one where I put it at, I think 6.2. And so just based on your judgment, what would you say this is going to belong to? Red, blue, or green? Red, right? And then the next most likely thing, if it's not red, would be green, and then blue is going to be the least likely, right? And so these are just the exact same things. We calculate the likelihood by taking in our coordinate 6, 2 and putting in the mean and the variance for class A, B, and C. The priors are all 1/3. The marginal is the sum of the likelihood times the prior for all of the different classes. And then we'll take the likelihood times prior divided by the marginal. Okay, and so here it says it's around 80% A, almost 0% B, and about 20% C with probabilities, okay? Here I just shifted a little bit, and I think this is 5.1. Okay, and now if I put this here, what would be your guess? So some say red, green, blue. I would probably go green, red, blue, but it's pretty close between green and red, right? This looks to be kind of the boundary between green and red. And so if we do these calculations, it turns out green is like 61% and red is 39%, and blue is, again, very close to 0. Okay, and so those are just some examples. And basically, you know, this is the Bayesian classifier. You calculate the likelihood, you multiply that by the prior, and in our case, the prior is the constant because we're assuming all 3 classes are equally likely to be drawn from. But again, you know, depending on your training data, you might say one of these classes is much more likely than the other. And that's fine, and that's going to be taken into account. And then and you do the appropriate calculations. Okay. Let me also kind of copy this image. So here we did Gaussian distributions, multivariate Gaussian distributions, which when we are calculating the likelihood, when you calculate the likelihood of the kind of the multivariate Gaussian distribution, you know, you're basically putting some. Yeah, we'll just stick. Okay, you know, you're putting some kind of mean value somewhere, and yeah, I don't know how to draw this. I'll just freehand, but this is kind of the, you know, the multivariate Gaussian PDF density or something. Over here we've got, that was not what I wanted. How do I reset this? Okay. Something that looks like this, okay? And then over here, we do try to model the kind of the covariance, okay? We capture the covariance between of x1 and x2 in kind of our sigma MLE estimate. Yeah, sigma ML, maximum likelihood estimate. Okay, and that's going to go, that factors in when we do this, right? So this is this likelihood portion. Is the multivariate Gaussian. Okay. Now, for the multivariate Gaussian, it's probably fine, and it's probably not too much of an issue to calculate the covariance. Okay. But it does require more data in order to, yes, question.
Just go over this, like, I guess, like, for the prior probabilities, like, they wouldn't be all equal to each other?
So the prior probabilities might not be all equal to each other if you believe that one of the classes are more likely to occur than another, okay? So, I don't know, if we were to take, I don't know, if we were try to guess whether someone is from California or another state or something like that. If we're selecting random students here at UCLA, we're going to put a higher probability that it came from California and we're not going to say all 50 states are going to show up with equal probability, right? So if we did, so like in the Senate, you might say a random selection, we're going to put all 50 states as kind of equal probability of being selected. Here on campus, we're going to put a much higher probability of being from California versus somewhere else, in like the House of Representatives, which is supposed to be proportional to the populations, then, California would have a heavier prior probability than something else. So here we're just assuming that all three classes are equally likely, but there might be other scenarios where you suspect that one of these classes is more likely than the others.
So in like this example, if there were like 100 red and like 50 blue, then the prior for red.
Right. Yeah. So I think, in the earlier example on Monday, I had like the bags from the different factories, and in our training data, most of the bags, or half of the bags, came from factory A and a quarter of the bags came from factory B. So we use that as our prior probabilities. Whereas if we had different knowledge and we knew that all three companies produced bags at equal rates or something like that, then we might say all three have equal probabilities. And that would affect your results based on kind of that prior information. Okay, so for the multivariate Gaussian, estimating the covariance matrix is actually not too terrible. Okay, you do need more data. Okay, you generally need more data to get an accurate estimate of the covariance matrix, but it's not too troublesome. But I want to kind of introduce kind of the idea of the naive Bayes classifier. Why do we put two dots over the I in naive Bayes classifier? But so anyway, we have the naive Bayes classifier, and this basically, the naive part of it is that we assume no correlation, no covariance between predictor variables. Okay. And we are aware that this is a bad assumption, okay? We assume no covariance between predictor variables, So the multivariate Gaussian will become equal to the product of independent Gaussians, okay? And so what we're effectively doing here, oh, I guess I already have this on my clipboard, is that when we're creating our things, you know, the ellipse to represent the multivariate Gaussian, this will have a, so this one already had no covariance, and this one also already had kind of no covariance, and basically they're supposed to, these lines are supposed to be perpendicular to each other, okay? Right? And this one used to kind of be at an angle, but now we are going to just assume that this is hard to draw. Okay? Looks like this. I probably actually need to something like this. All right, and it looks bad, and indeed it is, but overall, it still produces reasonable results, okay? So the biggest change is that this one, we no longer model this with covariance between x1 and x2. Okay, so the sigma, kind of the true sigma, is probably something like 3, I think 2.5, 2.5, and 3. And we're just going to, we treat it as basically 3, 0, 0, and 3, okay? And so the likelihoods end up being a little bit easier to calculate. You just because each variable is independent, you just take the univariate distribution of each variable and get the product of them, okay? So why would we want to do something like this, okay? If we know, you know, the ellipse that we fit to the green looks bad because it's assuming perpendicular, kind of there's no covariance and that these things are perpendicular, and we know that's not the case. But the reason why we might do this is that this significantly simplifies the number of parameters that we need to estimate. So with a two-dimensional multivariate Gaussian, we're really only reducing one extra parameter that we need to estimate, right? We got, as far as the variance goes, for the independent case, we have to estimate the variance of x1, the variance of x2, and the covariance between x1 and x2, okay? However, let's say you had some kind of data in 20 dimensions, okay? In 20 dimensions, you would have the 20 variances of each of those things to estimate, but then you would also have, I don't know, what's 20 choose 2? Like 190 covariances to estimate. You have to estimate between x1 and x2, x2 and x1 and x3, x1 and x4, and there's a whole bunch of different covariances that you're going to need to estimate. And depending on the amount of data you have, the covariances that you are estimating might be like, you know, subject to a ton of just random noise, right? So the more parameters you need to estimate, the more data you need to have, and that might not be a luxury that's available to you. And so by just assuming things are independent, you only have you don't have any of these covariances to estimate, and you can just take the product, which is a lot easier, and you don't have to worry about having poor estimates of the covariances between all of the terms. Does that kind of make sense as for why we would do this? Okay, so the multivariate Gaussian becomes the independent product of independent Gaussians, and then eliminates the need to estimate covariances between the x variables. Okay, and you know, for high dimensional data, there's a lot. Okay, so that's the naive Bayes classifier. Let's see. Okay, I think I've got time to go over this example. So a simple application, but it's kind of neat, is you can have a naive Bayes document classifier. Okay. And basically, in the English language, when we speak, there is a relationship between words, right? Sentences generally have like subject, verb, object, or some kind of thing, and generally a sentence won't consist of a whole bunch of nouns right in a row or something like that, right? There is structure in the language, but to put that in terms of numeric and mathematical terms, it's kind of difficult to kind of fully define, right? So, you know, in the naive Bayes document classifier, when we look at a sentence or a document or whatever, you know, we're talking about, we are going to just treat the words in the sentence as kind of independent, meaning the order doesn't matter, okay? The arrangement doesn't matter, and it's just, we're going to look at the words that appear. And so to say, he throws the ball is going to have the same kind of numeric representation as kind of, what did I say? He throws the ball, and would have the same numeric representation as like any other permutation of those words. So like ball, the, throw, he, or throws he, ball, the, okay? All of those would have the same numeric representation because we're just looking at the word itself and not kind of the order, not the arrangement, or not any kind of relationship between the words. We're just looking at how many times did this word appear, okay? And so this is called the bag of words model. It's as if you took, like, you can imagine, you know, having some document where the words are, and then like in a cartoon, you just shake it and the words fall off the page into a bag. And now the structure of the words and the structure of the sentences is lost, but the words themselves remain, okay? So the naive Bayes document classifier, we're going to use the kind of the bag of words model, which basically says the order or arrangement of words does not matter. Okay, basically only the words and their counts. The words and their frequencies matter. All right, and we know this is not how the language works, okay? We know this is not how English works. We know this is not the best model out there. However, for our purposes, it could still be useful, all right? It can still be useful in helping us classify some kind of word, and basically if you see, if you come across a document where the term Bayesian keeps appearing, okay, even though you don't know a lot about it, you can probably assume it's going to be related to Bayesian statistics or some kind of application, and it's probably has less to do with I don't know, politics or history or something like that, right? Because in those contexts, the word Bayesian is much less likely to appear, and in statistical contexts, the word Bayesian is much, something like that, right? And so basically, we're going to just say under this model, we would say for some quote class of document, we'll have a vector of probabilities for each word. A vector of, I would say, word probabilities. Okay, so for some class of document. So I just did a simple example. Okay. And basically, I took I used children's books because they have small vocabularies and are easy to work with. Okay, so I'm just going to kind of explain this as we go through the example, right? So I've got 3 children's books. We've got Green Eggs and Ham. Go Dog Go, and Are You My Mother? I don't know if you guys are familiar with these books. They are like American classics. Okay, and basically, in Green Eggs and Ham, it's is famous for being a book that uses only 50 unique words. And I don't remember what else, but basically, words like green and whatever, Sam will be will have high probabilities. Okay, and then in Go Dog Go, the word dog will have a high probability, and in Are You My Mother, the word mother is going to have a high probability. And this is almost like cheating, because basically if you come across, like, mother does not appear in these other things and stuff, but basically we want to be able to, we're going to take the sentences of these things, create some kind of document corpus that will inform us about kind of the frequency of the words, and we will use that to estimate our the likelihoods of some sort of I guess test document here. Okay, so let me so for example, if I open up Are You My Mother, it's about a bird who hatches out of his egg, and when he hatches, his mom's gone, and he goes out searching for him, and he talks to like a cow and a cat and stuff, right? And so it's going to say, it says, he went, where does it says? The hen was not his mother, so the baby bird went on. I have to find my mother, he said, but where is she? Okay, all right. So this is, this is the thing, and we're going to just treat, basically I just grouped some of these sentences together. I got rid of the punctuation, although there's, I think, tools in R that will do this. Here is Go Dog Go, and I guess this one's in all caps with some punctuation, and I'll strip that later. And so it says things like, the sun is up, the sun is yellow, the yellow sun is over the house, it is hot out here in the sun, it is not hot here under the house. All of these sentences are illustrated, by the way, and it says things like, the light is red. Oh, go dogs, go. The light is green now, right? They're driving cars. Okay, and so as humans, it's easy, right? if I give you this sentence and I say that now the cars stop and the dogs get out, and I ask you which book did this sentence come from? Yeah, you can easily tell which book that it came from, right? Okay, so anyway, I wrote up some code here. I want to clean it up before I kind of put it on CCLE. Okay, but we're going to do this. For some of you who took 102C, we did something similar, okay? Except in 102C, it was document clustering, okay? We did not have, in 102C, there was no labels provided, and we just asked the computer to kind of sort these into different clusters based on the words that appear, okay? Over here, it's a classification problem. We have labels in our training data, and using the labels in our training data, we want to see if we can identify a test case. So if that distinction is clear of what's happening, okay? So over here, I'm going to load up, let me clear out my environment. I'm going to load up kind of these packages that help text mining, and I'm going to go ahead and just read in our data, okay? And this is just to kind of put everything together into a data frame, and I create a corpus out of this, okay? And the corpus has a few tools to help everything along. So we're going to turn everything to lowercase. We're going to remove the punctuation, remove the numbers, remove stop words. Stop words are things like the and is and a. Things that are very common and are probably not very informative in general usage, okay? Stem the document turns words like runner, running, and runs, and run all into run, okay? So it just gets rid of word endings. Things like happiness and happy and I don't know, will just get turned into happy or hap or something. I'm not 100% sure the details of the stemming, but it basically, yeah, like happenstance and happens and I don't know, happening. I think we'll get stems to the same. I don't know if it'll. And maybe are those words related to happiness? I don't know. Okay. You're asking hard questions. Okay. But that's kind of the idea of stemming the document, and it's probably not 100% accurate, but it probably does a good enough job. That's kind of what we're doing with all of our models, right? We know the naive Bayes thing isn't 100% accurate, but maybe it does a good enough job. Okay. So after processing this, okay, I think, the original sentence in Green Eggs and Ham was something like, I do not like them in a box, I do not like them with a fox, I do not like them in a house, I do not like them with a mouse, okay. And after removing the stop words and stemming them, we get like box, like fox, like house, like mouse, like anywhere, like green egg, ham, like Sam. Okay. But it still kind of communicates what we're seeing there. Okay. So anyway, I'm going to turn this into a kind of a document matrix with word counts, right? And so when I do this, we get 32 by 93, which means we have a total of 32 kind of documents. Documents are just kind of like sentences that I broke the books up into these different chunks. And then, and we have 93 unique words that appear, okay? In general, the number of unique words that appear in your documents will probably be in the thousands, okay? But here I used children's books and I only used 3 of them, so we only have 93 unique words. And what we see is, so kind of the first, so these are all the different 93 words, and for the green eggs and hams, we can see words like anywhere, egg, green, ham, like, salmon, house appear quite frequently, but we have no words of happen, home. Okay, so that maybe answers our question. Happen, home, snort, plane, saw, those words don't appear at all. Whereas if I look at the kind of the tail of our document, I'm going to run out of time. Word counts. You know, green, eggs, ham, likes, salmon, house don't appear, but we get words like big and dog and now and old and saw and whatever. Okay, so so that's our entire corpus, and maybe I'm cheating a little bit because I'm doing the full thing into our document corpus, which is you'll see kind of different opinions on how you should do your document corpus, but I'm going to go ahead and just say for like green eggs and ham, we'll take the first 9. I broke green eggs and ham into 10 chunks, and I'm going to take the first 9 as the training, and then we'll use the 10th one as the test. Okay, and so to kind of get the likelihoods, I'm going to just look at kind of like the column sums of those the documents that appear in our 9 training cases. Okay, and so we can see words like anywhere, like, green, and ham show up very frequently. Words like and like shows up very frequently, and we also get good and goat and try and things like that. And so to kind of turn these into probabilities, I'm going to add, so we have a bunch of zeros, and zeros are problematic because in your training data, like the word, let's say the word little appeared 0 times in your training data, which means if a new document appears and it has the word little, if you're just using if you take 0 as kind of your probability, then any document that has the word little in it will be completely eliminated. It will have a 0 probability. So what I do is I'm just going to add like a small constant, like 0.1 or something, so that none of these have 0 probabilities. And I just turn the whole thing into a vector that will basically sum up to 1. So the word probability, after I add 0.1 and add them up, okay, the word like shows up with probability of around 19%, ham shows up with a probability of a little under 5%, and all of these other words that showed up 0 times show up with a very small probability, but a non-zero probability, okay? And I go ahead and I'll create kind of these word probability vectors for each of these kind of classes here, okay? And so, so now I have a word vector, okay? And I'm going to take kind of my test case. So my test case for green eggs and ham basically has anywhere, egg, green, ham, like, and sam, and things like that. And so so kind of, my test case, the document has, what did I say? Anywhere appears once, green appears once, and egg appears once, and let's just keep it at that. And basically, the likelihood, the naive likelihood, just assumes that this is going to just be the product of basically the probability of anywhere raised to the kind of count of anywhere. Okay, multiplied by the probability of green raised to the count of green. Multiplied by the probability, basically, of, word K raised to the count of word k in, in the document, okay? So it's just, it's basically a multinomial probability. So you're taking the probability of this word raised to its count, okay? And the probability of these probabilities, probability of word k, is going to be different for each class, right? So for green eggs and ham, the probability of like is going to be very high, and the probability of mother is going to be very low. Whereas for Are You My Mother, the probability of mother will be high, and the probability of egg, no, not egg, but ham will be low, okay? So, because I think egg actually appears in Are You My Mother? So we're going to calculate the likelihood according to the probabilities of each of their classes. And so we're going to have kind of the product, okay? And so I'm going to take each word probability from green eggs and raise it to, so test GE is basically the word count, and we're going to get words like will, with high frequency, and we have to raise the word probability to its frequency, okay? And so when we do this, because we're dealing with such a huge vector, we're going to get really, really, really tiny results, which might be okay, but sometimes it could result in something that's maybe too small, and we could run into kind of limits of kind of the floating point arithmetic. So this is the likelihood. We're getting things on the order of -37, -70, and -63, okay? And so, right here we see the probability that it belongs to green eggs, okay, as far as the likelihood goes, is on the order of, I don't know, 10 to the 23 times more likely, okay? So this is it. So here's our likelihood. Instead of dealing with the likelihood directly, it might be preferable to deal with the log likelihood. And so, so we would take the log probability, and instead of raising it to some power, the word count, we would just multiply it by the word count, and we would take the sum, okay? And we would get this. So these are the log probabilities, and we can see that if I take exp of this value here, indeed I get back kind of the original thing, okay? So as far as the log probability goes, to turn these back into probabilities, the marginal is equal to the sum of, I think the computer can handle this. And basically, it comes down to, because these are so many orders of magnitude much smaller, when we do the likelihood divided by the marginal, it's going to say its probability green eggs belongs to class green eggs and ham with probability 1, okay, after we plug that in. And we could try this for any of the other test cases that I've done. So this was the test case where the true class is from green eggs and ham, but I can plug it in for the Are You My Mother? Okay, and we can see, when we plug it in for Are You My Mother, this one ends up on the order of 10 to the -28, which is still about 25 orders of magnitude more likely than the other classes, okay? This is a little bit overly simplistic and a little bit extreme because the overlap between words is fairly low between the different classes. But this is a simple application that's still useful as far as the naive Bayes classifier, and it's possible because we've relaxed the assumption, or we've said we're going to assume there's no correlation between the words themselves, and we're just looking at the word counts, which simplifies our product estimations. Okay, we'll wrap up here for today, and we'll see you guys on Friday.